Now, on page 96, we're asked to find the sum of each. Looks like a pretty daunting task, but once you come to grips with the idea that these are following models that we're familiar with, then things start kind of cleaning themselves up a little bit. All right. So when you look at this, you might recognize this in form, especially with those factorials on the bottom, as something looking very much like a Maclaurin series or a Taylor series. So I'm going to rewrite it just to make it a little bit more obvious. But if I were to say 1 plus 1 over 1 factorial times 3 plus 1 over 2 factorial times 9 plus 1 over 3 factorial times 27 all the way up to 1 over n factorial times 3 to the nth, that might give you a better idea of what's going on here, especially when you look at the ones that follow. All right, we see here that we have a consistent progression in terms of our denominators. Our numerators, the numerators are always equal to 1. All right, so you start thinking about under what circumstances that happened before. And I could give you one example. 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus on and on and on and on and on. That is the expansion of the Maclaurin series for exponential e. All right, so once you make that recognition, then you're in really good shape. All right, and so the general term here would be 1 over n factorial x to the nth. All right, so now when you do a compare and contrast between the two, oops, I guess I could change color on my highlighter. You realize that the only thing that differs between the two is that x is equal to 3. All right, so if we know that this, what I wrote, the second line that I wrote is the series expansion that ultimately coalesces to be equivalent to e to the x, then the first one, if x is equal to 3, must coalesce to be equal to e to the third, and so therefore that must be the sum. So just by recognizing the type of series you're looking at, you can come up with the sum pretty easily. Like in the case of in part B, you see that we have an alternating series. All right, so alternating series involving odd values. It's like, all right, well, that could go a lot of different ways, but if you start narrowing it down to the more popular Taylor-Maclaurin series, you might settle on the sine function. So the expansion here, we would start off with the x, 1 over 1 factorial x to the first. We'd skip over the 1 over 2 factorial and go to 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth, and so on, with the idea being that we're looking for odd numbers, so 1 over 2n plus 1 factorial x to the 2n plus 1. So if we do, again, a compare and contrast between here and here, well, aside from the fact that I just whiffed and totally forgot to put the alternating component in there. Whoops. So negative 1 to the nth power. We wanted to start off positive. If we do that, then you see that the only thing that differs is that x is equal to 2. I'll write that somewhere else because we know that this is equal to the sine of x. All right. And so if we know x is equal to 2, then this must be equal to the sine of 2, and that would be the sum of this series. All right, so the next one, now we're in a different stratosphere a little bit, but nothing too crazy. You know, everything, you know, any kind of expansion that I would give you, I mean, anybody who teaches this course, you know, unless they're out of their minds, they would give you something that at least aligned with one of the rules that you learned. Or at least you could build by combining, adding, subtracting, you know, using the rules for sequences and series to combine, you know, like substituting into a Maclaurin or multiplying by a Maclaurin or something like that. But the bottom line is it should be recognizable. And in this case here, we have something that's alternating. Yeah, that's wonderful. But we have a common ratio of negative 2/3. If you think about it, going from each term to the next, you're multiplying by negative 2/3. All right, so then we just go back to what we've been kind of living with over the previous pages. That's going to be equal to 1 over 1 minus 1 over. It's going to be 1 over because that's what it is in this case. By rule, it's a sub 1 over 1 minus r. But in this case, it's going to be 1 over 1 minus the r value is negative 2/3. So 1 over 1 plus 2/3. So that's, you know, 3/3 plus 2/3 is 5/3. 1 over 5/3 is 3/5. So that would be your sum because this is a geometric series. All right. So those are a couple of quick hitter problems, you know, quote unquote quick hitter problems, but just to kind of bring together the stuff that we've been talking about, but also to give you a sense of, you know, how that stuff can be applied. Right. The theorem below actually has nothing to do with the stuff we were talking about. All right. This has to do with the stuff that comes up on the next page. I just couldn't fit it on the next page, so I chucked it in over here. So if you're working with a power function, then you can differentiate and integrate, and it's pretty easy. You just integrate or differentiate the individual components, which in most cases, well, for power series in all cases, but in other types of series, it kind of gets a little iffy, but in most cases it boils down to applying calculus rules to your sum formula, because really, if you think about a summation, it's really just adding different terms together. So when you take a derivative or an antiderivative, you can take the antiderivative or the derivative term by term and add it all together later. All right? Or you could do it all in one shot and you know, differentiate around the sum like you would, for example, like a chain rule case where you have, you know, the exponent that has a sum inside of it. You know, so there's a lot of different calculus rules that can come into play, but for this, we're just focusing on the power relationship. And so so that's pretty nifty because we can work term by term, or we could work with the summation, and we're going to talk about that. Now, the convergence interval, that's where things get a little dicey. The radius of convergence of the series obtained by differentiating or integrating a power series is the same as that of the original power series. However, this is what happens. The bounds could be a little iffy. All right? So the radius will be the same, but the interval can differ because of the fencing. Right? A bracket may become parentheses or the other way around. Right? But the key component is, or two components, you can't gain an endpoint by differentiating, and you can't lose an endpoint by integrating. All right, so if it was an endpoint before you integrated, it will still be an endpoint. So if it was a bracket before you integrated, it'll be a bracket after you integrated. All right. But if you're differentiating, if you had parentheses, there's no circumstance in which that'll ever become brackets. All right. So those are some nifty things to keep in mind. All right. So you can't gain or lose based off of the process of integrating or differentiating the bounds, or the gain or lose the bounds based off the act of integrating or differentiating. So that's going to bring us to page 97.